Hello, everyone. This talk is about our new paper on noisy broadcast networks. I shall first define what is a noisy broadcast network. I will then state our main result, which has matching upper and lower bounds for noisy broadcast networks. And we'll finish with an overview of the techniques. So let's start. A broadcast network, also called a shared blackboard model, is an n-party communication channel where each party has its own input. If n equals to 6, then you have 6 parties and party I has input xi. And together, these 6 parties want to compute a function f of all the inputs, which means they want to know f of x1, x2, all the way up to xn. The way they compute this function is by running a communication protocol. And over a broadcast network, a communication protocol proceeds in several rounds. And in each round, there is a pre-specified party, which is the speaker for that round. In this round, the speaker uses his input, any messages he received so far, and any randomness he has to compute a message that he sends in this round. And then this message is received by all the other parties in the system. Crucial to a broadcast network is the fact that the same message is received by all the other parties in the system. This is different from some other communication channels where the same party in the same round can send different messages to each of its neighbors. In the broadcast network, that's not the case. Every round has only one speaker, and the speaker sends exactly one message, which is received by all the other parties in the system. Okay, this is the broadcast network. Let us now define a variant of it, which is the noisy broadcast network. Everything in the noisy broadcast network stays exactly the same, except that there is stochastic noise. Now, when this party decides to send a message, then the message is received correctly with probability 1 minus epsilon. And with the remaining epsilon probability, the message is received incorrectly. For example, if this party were to send the bit 1, then with probability 1 minus epsilon, independently for each party in the system, they will receive the correct bit, which is 1. And with the remaining epsilon probability, again, independently for each party in the system, and also independently across all the rounds in the protocol, they will receive the incorrect bit, which in this case is 0. And the presence of this noise is what is why we call it the noisy broadcast network. Okay, we now have two models. We have the broadcast network and we have the noisy broadcast network. And clearly, noise can only hurt a protocol. So any protocol that works over the noisy broadcast network also works over the noiseless broadcast network. There's also a transformation in the other direction. We can show that if you have a protocol in the noiseless broadcast network, and we shall assume that all protocols are polynomial in length, this is the parameters range that we are interested in, then with an overhead of O of log n, which means by the multiplicative overhead of O of log n in the number of rounds, you can get a protocol that is equivalent and works in the noisy broadcast network. Why is that? This is because you can take each round of the original protocol and you can repeat it log n times in the noisy broadcast network. Because the noise is independent for each of the rounds, the only way the majority of these rounds fail is if there's a lot of noise in at least half of these O of log n rounds, which happens with probability that is polynomially small. So one round fails with probability that is polynomially small in n, and this allows us to union bound over all the rounds in the protocol and all the parties in the system, and yet that the simulation is correct for all the rounds and all the parties except with probability polynomially small in n. An equivalent way to state this easy lemma is that it shows that the interactive coding overhead for the broadcast channel is at most O of log n. That is, there is a way to transform any protocol in the noiseless channel to a protocol in the noisy channel that has the same functionality with an overhead of O of log n. But is this O of log n tight, or can we get a better interactive coding result? Gallagher in the 80s showed that for a restricted set of protocols, which I will call non-interactive and I shall define later, you can actually get a much better overhead. You can get an overhead of O of log n. And in fact, Gallagher showed this is the case for exactly one protocol, which is a protocol for the identity task. In this task, all the parties have a bit as input. So party I has a bit xi as input, and they want to know all the input bits. They want to output x1, x2, all the way to xn. And for this task, Gallagher showed that there is a noisy protocol, a noise resilient protocol that has an overhead of O of log n. And therefore, it means that at least for this task, this O of log n overhead is not tight. Can we do even better? In 2008, GTS showed that for the identity task, Gallager's protocol is optimal, which means they showed that there is no protocol that has an overhead of smaller than log n that solves identity over the noisy broadcast channel. Because this is a lower bound, it also implies a lower bound on interactive codes. And for this problem of finding the overhead of interactive codes over the broadcast channel, the best upper bound is O of log n. This is the easy lemma I explained. And the best lower bound is omega of log n, which is the result by GTS. And therefore, there's a gap between the log n overhead, which is the best upper bound, and the log n overhead, which is the best lower bound. This is where my work comes in. We close this gap and find the right answer. And we show that the interactive coding overhead for the broadcast network is root log n. So it's neither the previous best upper bound of log n, nor is it the previous best lower bound of log n. It is exactly in the middle. And the fact that it's different for both of these known results means that we have to show a new upper bound and a new lower bound for the overhead. And this is what we do. Our bounds match at root log n, which is also interesting because tight interactive coding bounds are known for many different channels. And for all of these channels, there's one of two phenomena that happen. One phenomena is that you have a constant overhead interactive code, which means that basically noise does not affect this channel a lot. You can pay a constant in the length of the protocol, and you can get a noise resilient version of any protocol you want. And these are the first type of channels, which are easy when it comes to making protocols noise resilient. The other type is channels that have a log n overhead. And this is the worst possible because, like I said, if you repeat a message log n times, and you decode by majority, then the decoding is correct, except with probability polynomially small n. And usually this means that you have a protocol, you have an interactive code with overhead log n for any communication channel. So log n is the worst possible, and we know many channels that have this behavior. Constant is the best possible. We also know many channels that have this behavior, but we show that this broadcast network is the first channel with a tight overhead in between O of 1 and O of log n. And this is pretty interesting. Moreover, when we show the lower bound on our interactive coding overhead, then we show a lower bound for a protocol that actually computes a Boolean valued function. And this makes progress towards an open question posed by Yao in 97, because it doesn't really solve the open question because he was looking at another setting of parameters, but it does make progress in that direction. Okay, so that's the main result. We have an interactive coding upper bound of root log n for the broadcast network, and we have matching lower bound. And now I shall go over the techniques behind these two results. For the rest of this talk, I will restrict attention to one particular form of a noiseless protocol. I will only consider a noiseless protocol that has n rounds, which means the number of rounds is the same as the number of parties. And moreover, I will be assuming that party I is broadcasting in round I. So the speaker for round I is party I. This is without lots of generality, but it does not really hurt me in this talk because the point here is to get all the ideas across, and all of them appear even in the subcase. So this is the protocol we shall be working with. It has n rounds, party I speaks in round I, and let us first see what is the upper bound. For the upper bound, I want to show that you can simulate this n-length protocol with an overhead of root log n, which means a total of n times root log n rounds with some small error probability, 1 over poly n. Okay, our goal is to simulate n-length protocols in n root log n rounds with error probability 1 over poly n. And the first thing I want to explain is that in order to do this, it is sufficient to simulate chunks of length k, where k is root log n, in k square rounds, which is log n because k is root log n, with error probability 2 to the minus k squared, which is 1 over poly n. And the reason this is sufficient is because you can take your n-length protocol, you can break it into chunks of length k, and you can apply this simulation with k square rounds on each chunk. This would mean your overall protocol has length n over k times k squared, which is nk, which is n root log n as desired. And also the whole simulation is direct because each chunk is direct except with probability polynomially small n n. 2 to the minus k squared is polynomially small n n. And they are n over k or less than n chunks that we are simulating. And we can union bound over all of these chunks and still get an error that is 1 over poly n. Okay, so this is the first claim. To get our overall upper bound, it is sufficient to focus on k-length chunks and simulate them in k-squared rounds with error probability 2 to the minus k squared. And let's see how we do this. We need to simulate k-length chunks in k-squared rounds with error 2 to the minus k squared. And it is crucial here that the error guarantee that we are going for is super low. And it is so low that it is actually the lowest you can hope for. If you have a k-squared round simulation, because the noise in any round is constant, with probability 2 to the minus k squared, every round is erased in the whole protocol. And therefore, you cannot hope to get error that is smaller than 2 to the minus k squared. And asymptotically, this is what we get. So our error guarantee is the best possible. And this is what makes the simulation hard. Because even if the error was slightly larger, even if you change the polynomial inside the exponent from 2 to the minus k squared to 2 to the minus k, then the task becomes easy. You simply repeat each round, each of the k rounds of the original protocol k times. Then you can say that with except with probability 2 to the minus k, the majority is correct, and you can union bound over everything. Everything works out, and you get 2 to the minus k error in k square rounds just by repetition. 2 to the minus k is easy. 2 to the minus k square is what we are going for. And as a first step towards this, I will actually explain the idea in Gallagher's paper. I will show that for a restricted set of chunks, which are non-interactive, you have a much stronger result. Instead of having k squared rounds and 2 to the minus k squared error, you have k roughly rounds and 2 to the minus k error. This is stronger because if you repeat this k times, the rounds become k squared, the error becomes 2 to the minus k squared. So you have a stronger result for non-interactive chunks. And let us see what this is. So first, let us see what is a non-interactive chunk. I will say a chunk is non-interactive if the symbol broadcast at any round during the chunk is independent of all the symbols that were received before. Put another way, if the model allowed it, a non-interactive chunk could have been executed simultaneously. This is because all the parties already know what they have to broadcast. And if the model allowed it, they could just send these symbols at once. And therefore, a non-interactive chunk is a simultaneous chunk. And let us see how we simulate such chunks with this strong guarantee. This will be a three-stage simulation. In the first stage, which I will call broadcast, all the players that are speaking, all the k players, simply broadcast their symbol log k times. This takes total of k log k rounds. And by standard concentration inequalities, this guarantees that if players decode by majority, then everybody gets all of these symbols correct, except with error 1 over poly k. Okay, these are the first two stages. And after this stage, I have a very strong guarantee. I know that any player in the system knows all the k bits with error, except with error 1 over poly k. But this is not what I claimed. I claimed that the error is 2 to the minus k. So what is left is to boost this error down from 1 over poly k to 1 over 2 to the minus k. And to see how we do this, imagine that there was a magical player that actually knew all the bits directly, for which the error was 0. Then here's how all the other players get this low error. This magic player who knows all the bits directly, he takes all these k bits and encodes them using an error correcting code, which takes, let's say, k to 10 k bits, and he sends this encoding. Now, because this error correcting code has constant distance, the only way the parties do not decode these bits directly, the 10 k bits that were sent by this magical player, is if a constant fraction of them were incorrect. But to have a constant fraction of incorrect bits, you need error probability 2 to the minus k. So if you had a magical player, then all it needed to do was to send an error correcting code of all the symbols he had after stage yes. And then every other player in the system will decode correctly except with error 2 to the minus k, and we will be done. However, we do not have any magical player. All we have is a lot of players, each with an error probability of 1 over poly k. So how do we get around this? The way we do this, or the way Gallagher does this, is to do the same error correcting code trick, but this time do it distributedly over many players. Again, each player has k bits. They will encode them using an error correcting code. So each of them now has 10 k bits. And player 1 will send the first 10 bits of his encoding. Then player 2 will send the next 10 bits of his encoding. Then player 3 will send the third set of 10 bits of his encoding, and so on until the last player sends the last 10 bits of his encoding. And I want to claim that the thing that the players send distributedly actually looks a lot like a legitimate encoding of an arithmetic encode of the K symbols that they wanted to encode. The reason is the only players that ever send the wrong symbols during this broadcast is the players that did not have the right guess of the right guess in stage 2. And for each player, the right guess happens except with probability 1 over poly K. So the only way a lot of the K players, a constant fraction of the K players did not have the right guess is if all of them had this 1 over poly K error. But if all of them had this 1 over poly K error and we have independence across players, this means that the total error probability is actually 2 to the minus K. And we can say this in the converse, except with error 2 to the minus K, the symbols that are broadcast by these K players in the distributed manner resemble an error threatening code. And we can do the same argument as before to get that, except with probability 2 to the minus K, everybody receives all the symbols directly. Okay, so this is Gallaghers protocol. It works for K length chunks and it gives a very strong guarantee that is K log K rounds and error 2 to the minus K. Now we want to extend this protocol to general chunks, which may not be non-interactive. And we are settling for a weaker guarantee, which is K square rounds and 2 to the minus K squared error. So let us see how we do this. The crucial observation in this part is that even if you have a general chunk that may not be non-interactive, the first message in the chunk is still non-interactive. This is because the first message does not have any messages before it, and therefore it cannot depend on any of the previous messages. So even if you had a general chunk, for the first message in that chunk, you can do the same argument and say that this first message is direct with probability 2 to the minus K. Okay, so we have the first message. How do we get the remainder of the messages? Here is how. What we want to do is we want to run this Gallaghers trick K times, hoping to get one extra message each time. So for the first time, the first message is non-interactive and we get that except with a very small error probability. Then we shall assume that this is correct. And then the second message will actually be the first message. And then we will get that one with probability 2 to the minus K and so on and so on. The problem is 2 to the minus K is not 2 to the minus K squared. It is much larger. And therefore, sometimes some of these messages that you add will fail. And we need a mechanism to detect these failures and then correct them as needed. And for this, we use a very standard, not really standard, but fairly a by now standard rewind if error framework that tries to get each bit and correct the bits that are incorrect. So you start with an empty transcript. This is pi that you start with. This is empty to begin with. Then you run one round of Gallaghers protocol. This gives you a symbol sigma. This is the first symbol in the remainder of the chunk. And pi comma sigma is a transcript that is one longer. Then you try to check if this pi comma sigma is correct. I will not explain how they do this. It can be done. It is a non-interactive subroutine that one can execute. But the point is you have this extra symbol in pi, then you see if this extra symbol is correct or not. If it is correct, then you add the symbol to pi. And now your pi is one longer, so you made progress. If it is incorrect, then there may be an error in sigma, or maybe you had some error in pi that you did not detect. And when this happens, you delete sigma, and you also delete one symbol from pi. So now pi is one shorter. And then you keep going this way. In each stage, with probability 2 to the minus K, you either add one correct symbol to pi, or you delete one incorrect symbol from pi. And therefore, in each case, except with probability 2 to the minus K, you make one unit of progress. And if you do this K times, then except with probability 2 to the minus K squared, you will be at least order K units of progress, or a constant fraction of the time you will be making progress. And this means that if you do it order K times, then after you have done all these iterations, then you will have a transcript of length at least K, and you would have simulated the chunk correctly. Okay, this is the upper bound. You start by an upper bound from Gallaghers, which shows a very strong result for non-interactive chunks. Then you go from non-interactive chunks to general chunks using this rewind if error framework that keeps adding one extra symbol every time, checking whether it's correct or not. And if it's incorrect, you delete it. And you do it order K times so that if you make progress a constant fraction of the time, you will still have K symbols at the end and you will have simulated the chunk correctly. This is the whole upper bound. It finishes everything I wanted to say about this. I also had some slides on the lower bound, but I don't think I have time to go over that. So I will stop here. I'll just recall our main result. I defined the noisy broadcast channel. Our result was a matching upper and lower bound showing that the interactive coding overhead for this broadcast channel is root log n. I explained how the upper bound works. The lower bound I have slides for, but I would just refer you to the paper. And yeah, thanks for listening.